All right, let's get right into it. We're about to explore one of the most fundamental rules of our universe. It's this invisible force that literally governs everything, from a tiny spark of static electricity all the way to the atoms that make up you and me. This is the story of Coulomb's law.
To really get a feel for this law, we've got to start big. I'm talking really, really big. So let's kick things off with a powerful and very visible display of electric force out in the wild.
We've all seen it, right? A bolt of lightning just tearing across the night sky. It's just this raw, incredible display of power. But what you're actually seeing is a giant electrostatic discharge. And believe it or not, it's all driven by the exact same tiny forces we're about to break down.
So that brings us to the big question. How do you get from the microscopic world of particles to something as mind-blowingly dramatic as a lightning bolt? What's the fundamental rule book that electricity follows? Well, to find that rule, we first have to meet the main characters in our story. And it all starts with a basic property of matter itself. We're talking about electric charge.
So what even is electric charge? The easiest way to think about it is like mass or color. It's just a basic property that some particles, like electrons and protons, are born with. It's just part of who they are, and it's the source of pretty much all electrical phenomena. Now, here's what's so cool about this. In the entire universe, we've only ever found two kinds of charge. That's it. We just call them positive and negative. Protons have a positive charge, electrons have a negative charge. Simple as that.
And from these two simple types of charge, we get the very first and probably the most famous rule of electricity, one you've definitely heard before.
And here it is. It's a fundamental dance of the universe. If charges are the same, two positives or two negatives, they push each other away. They repel. But if they're different, a positive and a negative, they pull toward each other. They attract. This simple push and pull is happening everywhere, all the time.
Okay, besides that whole push and pull thing, there are two other really crucial ideas we need to know. First, charge is conserved. That means you can't just make it or destroy it, you can only move it from one place to another. And second, and this one's a little weirder, charge is quantized.
Quantized? Yeah, I know, it sounds a little intimidating. But the idea behind it is actually pretty simple. It just means that charge isn't some smooth, continuous fluid. Nope, it comes in tiny, individual little packets. And this is the size of that packet. This incredibly tiny number is the fundamental unit of charge. It's the charge of one single electron or one single proton. Every bit of charge you'll ever find, anywhere, is just a whole number of these things. You can have 1,000,000 of them or 2 of them, but you can never, ever have half of one. All right, so now we know what charge is. We know there are two types, and we know how they behave. So we are finally ready to uncover the law that puts a number on that push and pull, the rule that lets us actually calculate the force between charges.
And here it is. This is Coulomb's law. It's the mathematical formula that tells you exactly how strong the force is between two tiny charged particles that are just sitting still.
So how does it work? Well, it's really built on two simple rules. The first one is super intuitive. The more charge you have, the stronger the force. Two really charged particles are going to push or pull on each other way harder than two weakly charged ones. Totally makes sense, right?
Now the second rule. This is the real game changer. It's all about distance. As you pull two charges apart, the force between them gets weaker. But here's the thing. It doesn't just get a little weaker. It falls off a cliff.
This is the secret sauce right here, the inverse square relationship. So what does that mean? It means if you double the distance between two charges, the force doesn't just get cut in half. No way. It drops to 1/4 of what it was. And if you triple the distance, the force plummets to 1/9. This is why these forces are so incredibly powerful up close, but they fade away so quickly as you move apart.
So now let's zoom back out. With this law in our back pocket, we can start to make sense of the entire world of stationary charges. This whole field of physics has a name: electrostatics.
And electrostatics is exactly what it sounds like, right? The study of static or non-moving electricity. And Coulomb's law? That's the cornerstone. It's the foundational rule that makes the whole thing predictable. And I promise you, this is not just some abstract physics concept. This law explains that super annoying static cling you get in your laundry. It's why a balloon sticks to a wall after you rub it on your hair. But even more profoundly, it's the attractive force that holds every single atom in your body together. It's literally what's holding you together right now.
So there you have it. Coulomb's law gives us the complete instruction manual for charges that are sitting still. But that leaves us with one last, really tantalizing question. What happens when they start to move? Well, when they do that, a whole new, incredible force enters the picture, and we call that one magnetism.